Hello everyone, my name is Dan Jia and I'm from RWTH Aachen University. I'm presenting our work Self-Supervised Person Detection in 2D range data using a calibrated camera. This work is in collaboration with Matt Steinweg, Alex Herman, and Bastian Leiber. 2D LiDARs, also known as laser scanners, are useful sensors for many robotic applications, including person detection. They give accurate distance measurement with long sensing range. Compared to cameras, they have a much larger field of view, typically greater than 200 degrees. In addition, they are usually mounted at close to ground level, which is very easy for robot design. Cameras, on the other hand, need to be mounted high enough such that the images have a natural viewing angle, and that is not always possible. Last but not least, they are already commonly available on many robotic platforms, particularly for meeting safety requirements. So we are interested in detecting persons with 2D LiDAR. More concretely, the task is, given a 2D range data, we want to find XY locations of all persons in the scene. There are already good solutions to this problem. In particular, in our previous works, we built two deep learning-based detectors, JO3 and DRSpam, which achieved the state-of-the-art results, and we have successfully deployed these detectors on multiple robots. We open sourced our code for the community and it includes a ROS node. You can find out more on this GitHub page. However, one limitation we found with these detectors are with their generalizability. During the actual deployment, there are likely to be different LiDAR models for different robots, and the LiDARs are likely to be mounted on different height. This will alter the patterns in the scan. In addition, the robots will likely be deployed in different environments. Generalizing from training to testing is a typical problem for learning-based detectors and can be addressed by having sufficient diversity in the training data. That is the case for image-based detectors, where the community has over the years collected abundant amount of datasets. However, for 2D LiDARs, there are at the moment only 2 annotated datasets, falling far short from the diversity that is needed, and it is very hard to annotate LiDAR data. So we ask ourselves this question: is it possible to automatically generate training labels for a 2D LiDAR-based detector using a pre-trained image-based detector? We call these labels pseudolabels because they are automatically generated rather than manually labeled. There are many application scenarios where this could be useful. For example, we could generate pseudolabels while the robot is operating and use them to improve the LiDAR-based detector, which gives us detections in a much larger field of view. Or for some applications, privacy is a concern. In those cases, we can have an initial training period with a camera attached to the robot and remove it for the actual deployment. The robot will still have person detection capability. So the short answer to this question is yes, we can generate such pseudolabels, and that's what we will demonstrate in this work. As a teaser, here on the left, we show as green circles output of a detector trained with annotations using a different dataset. And on the right, we show output from the same detector, except it is trained using pseudolabels on the same dataset. The improvement is clearly visible. So how do we generate pseudolabels? For illustration, here is an image with projected LiDAR points. We first obtain bounding boxes using the image-based detector. From all boxes, we select a subset that has high detection confidence, proper aspect ratio, and does not overlap significantly with other boxes. For each box, we take the LiDAR points that fall within its frustum. Our goal now is to find the location of the person. We accomplish this with a simple two-step heuristic. We first run a k-means clustering in the range space with k equals to 2. This step gave us a rough foreground and background separation. Then we find the point that is closest to the foreground cluster center, and starting from that point, we perform a mean shift, and the result is used as a location of the person, and the nearby points are used as a positive pseudolabels. For the negatives, we take LiDAR points that do not belong to any bounding box. We discard all the other LiDAR points which falls within boxes that are not selected for generating the positives, since we cannot confidently infer their identity. So we found this simple approach works well in practice thanks to the strong prior provided by the bounding box. Here are some examples. We also identified some common failure cases. The persons may be occluded or very close to the background, which gives poor localization, extremely sparse scan at far distance, or misalignment between LiDAR and camera. To handle these potentially noisy labels, we experiment with two existing robust training techniques. First is a partially Hooverized cross-entropy loss, a noise-tolerant loss function. Second is a mix-up regularization. It generates training samples by linearly mixing both the input and the label of two data points, thus encouraging convexity in the latent feature space. Here are qualitative results. The green circles and orange dots are positive and negative pseudolabels, and the red circles are ground truths. We see that pseudolabels don't cover all persons in the scene. This corresponds to our design choice where we favor the correctness of the labels over their coverage. Now we show the output of a JAWS-3 detector trained using pseudolabels. Note that the detections have good recall, even though pseudolabels we use for training don't cover all persons in the scene. Here's another outdoor sequence. First, the pseudolabels. Now the detector output. For quantitative analysis, we use the publicly available Jackrabbit dataset, which is collected using a mobile robot with a suite of sensors. In particular, we use a 360-degree range scan coming from the two 2D LiDARs at the base of the robot, as well as the official faster RCN detections included in the dataset. We conduct a series of studies, each aiming to answer one particular question. The first question, are the pseudolabels valid? To study that, we match pseudolabels with ground truths and compute their true positive and true negative rate. We found that both the positives and the negatives have a true rate higher than 90%, proving their validity. As an ablation study, we also generated pseudolabels using the actual annotated 2D boxes and found similar results. This shows that pseudolabels are robust to the noise in the detection boxes. Next, we want to know if the pseudolabels reflect the distribution of persons in the dataset, or rather they will introduce some bias. We plotted the distance histogram of pseudolabels on the left axis and the actual 3D annotations on the right. Overall, these two distributions share a similar shape, other than a small difference at 2 to 3 meter range. So we conclude that pseudolabels don't introduce strong distance-related bias to the training. Then how effective are training with pseudolabels? We trained multiple JAWS-3 and DR spam detectors using different supervision and compare their average precision. First, we have the ones pre-trained using a different dataset. Next, we have the ones trained from scratch with pseudolabels, and we found a more than 6% improvement on AP. Fine-tuning would give even slightly higher scores. For comparison, we also trained with the actual 3D annotation, and these gave the best results. Notice that the gap between the pre-trained to the pseudolabels is greater than the gap between pseudolabels to 3D annotation. These numbers show that using pseudolabels for training are very effective. Can we further improve pseudolabels to reduce the gap to annotation? We answered this question in 2 steps. We saw that pseudolabels contain noise, so in the first step, we studied how much does the labeling noise influence detectors. We use the ground truth annotations to incrementally remove the noisy labels from training. So if we remove all misclassified labels, we have more than 3% improvement. Correcting localization error on top of that gives more improvement for DR spam. These values are upper bound of using pseudolabels. The remaining gap to annotation is due to reduced diversity in training examples. Of course, during deployment, we don't have annotations to clean pseudolabels, but we can use robust training to limit the influence of labeling noise. Vanilla, Joe3, and DR spam are trained with cross-entropy loss. Adding mix-up regularization gave us mixed results, but the changes are small. Partially Hooverized cross-entropy loss gave consistent improvement for both detectors. Combining both techniques also gave improvements to both detectors. So these numbers show that combining pseudolabels and robust training, we can get detectors that are almost as good as using clean pseudolabels without using any annotations, and they are much better than the pre-trained ones. So to summarize, in this work, we proposed a method to train a 2D LiDAR-based person detector without any manual labeling. Our method generates pseudolabels using a camera and an image-based detector, and these pseudolabels can be used to improve the detector during deployment. Please check out our code on GitHub, and thank you for watching.